Hello friends, welcome back to Rising Mathematics. In this video, we are going to solve this question from linear algebra based on the concept of basis and dimension. Question is, let S be the set containing numbers 0, 1 up to n and V be the vector space of all functions with domain S and codomain set of real numbers over the field of real numbers. Find a basis for vector space V. What is the dimension of vector space V? We will start our solution. It is given that S is the set containing numbers 0, 1 up to n and V is the vector space of all functions with domain set S and codomain set of real numbers over the field of real numbers. Now we need to find basis for this vector space V. For this, consider functions fi from set S to R as fi of j is 1 for I equals to j and fi of j is 0 for I not equals to j, where this I and j are numbers from set S, hence they range from 0 to n. Now we will claim that the set B containing functions f0, f1, f2 up to fn forms a basis of vector space V. Now, in order to show that B forms a basis for vector space V, we need to show that these functions f0, f1 up to fn are linearly independent and set B spans the vector space V. So, we will do that. Now, to prove f0, f1 up to fn are linearly independent. For this, consider this linear combination a0 f0 plus a1 f1 plus and so on plus an fn equals to 0 bar, where this 0 bar is the 0 function. 0 function is the function for which image of every element is 0. Now, consider 0 in set S. Then we have image of this 0 under this linear combination is equal to image of 0 under 0 function. Now, image of 0 under 0 function is clearly 0 and this LHS becomes this. Now, note that f1 of 0 will be 0, f2 of 0 will be 0, similarly fn of 0 will be 0. So, all these upcoming n terms will be 0, so we get this. Now, we know that f0 of 0 is 1 by definition of fi. So, we get a0 1 equals to 0. Now, 1 is not equals to 0, so we must have a0 equals to 0. Now, again, instead of 0 in S, consider 1 in S. So, here we get image of 1 under this linear combination equals to image of 1 under 0 function. Now, image of 1 under 0 function will be 0, so RHS will be same. Now, here we get instead of 0 all over there will be 1. So, a0 f0 1 plus a1 f1 1 plus and so on plus an fn 1. Now, clearly f0 of 1 will be 0. Here f2 of 1 will be 0. Similarly, here fn of 1 will be 0. So, this f0 of 1 will be 0. Next term f2 of 1 will be 0. Similarly, fn of 1 will be 0. So, all these terms will be 0. So, we will get a1 of f1 of 1 equals to 0. Now, here for a1 of f1 of 1 equals to 0, f1 of 1 will be 1. So, we get a1 1 equals to 0. Now, 1 is not equals to 0. So, we will get a1 equals to 0. So, in this way we have found that a1 equals to 0. So, continuing in this way, for 1 to up to n in set S, we will get a1 equals to 0, a2 equals to 0, similarly an equals to 0 respectively. So, as all these coefficients comes out to be 0, vectors or functions f0, f1 up to fn are linearly independent. Therefore, the set B is linearly independent set of vector space V. Now, to prove that span of f0, f1 up to fn is V, consider a function say h in vector space V. Then, for this function h, we have h of 0 will be r naught, h of 1 will be r1, similarly h of n will be rn. Okay, so it is possible that Ri is equal to Rj for some I and j ranging from 0 to n. So we have considered one function from vector space V, and we have image of 0, 1 up to n under this function h, that are R0, R1 and Rn respectively. Then note that this function h is a linear combination of f0, f1 up to fn, as h equals to r0, f0 plus r1, f1 plus and so on plus rn, fn. Now how to verify this thing? We will find image of 0 under h and image of 0 under this linear combination, both will be same. So image of 0 under h is r0, here we have this thing. Now image of 0 under this linear combination will be this, which can be written as r0 of f0 0 plus r1 of f1 of 0 plus and so on plus rn of fn of 0. Now all these f1 0, f2 0, similarly fn 0 will be 0, so all this term will get vanished. So we will only get r0 of f0 of 0. Now f0 of 0 is 1 from definition, so we get r0 1, and hence image of 0 for this linear combination will be r0, which is equal to image of 0 under h. So this is the verification for h is the linear combination of f0, f1 up to fn in this way. Now we can verify for all remaining numbers 1, 2 up to n of h, and therefore h will be an element in span of f0, f1 up to fn. Now as h is any arbitrary function in this vector space V, so we can conclude that our vector space V will be span of the functions f0, f1 up to fn, and thus set B spans the vector space V, which is also linearly independent, and therefore set B containing functions f0, f1, f2 up to fn will form a basis of vector space V. Now as cardinality of set B is n plus 1, as there are total n plus 1 functions here, therefore dimension of vector space V will be n plus 1, since we know that dimension of vector space V is number of elements in its basis. And this completes our solution.